so you guys know, I want you to try to keep the hardware in the kits until the second half. It's a little bit different. I usually run this a lot more time constrained, and I try to just, like, jump people onto the hardware. But I actually want you to try to pay attention to me. Crazy thought, but because the hardware is far more interesting than I am, and I'll completely lose you. So, if you could wait. Yes. Not necessarily, but you were coming for the workshop and pre-registered. The prerequisites included Linux laptop with 100 gigabytes, like all this stuff, and the RAM and all that stuff. And then other than that, you just talked to Beyond about getting the hardware for the kit for this. Okay. So as far as the network, there is Wi-Fi in here. The password has to be net, but it's not. It shouldn't be required for this. What's that? I believe it's all lowercase. I get to cheat standing up here. Hey. Show and tell. Yeah, you're not going to bother me that way, but that's my fault. So. the hardware than I am, so I'll try to bore you to. Just realized my laptop's not plugged in. Display. The base computer. I haven't used phone stuff. All right. I've actually I was on the slides up here, and I just pushed E-ALE. Slides are up there right now. I pushed this latest version after I was wrapping up here, so you'll see the slides folder. So go there. ALE, and you can see the slides. What to do is and what Beagle, and hopefully get you all to the point that you're interacting. This is Jason Kridner, employee. A few months ago, I decided to pursue a passion project. Org, at the company as kind of a skunk works thing. At this point, TI just spend 98 time. So it's really they allow me to just focus on it completely. Benefit for TI is obviously people use them and benefit for me I think is pretty obvious. I have the coolest job in the world. People create cool. So it's 10 years this year. 2008 was when we started up what BeagleBoard, and all the kids and everything. I said they're all published on creative. What I wanted, the basic structure of what I'll be going over, to give you the more than the other big component. Design. Picked up these boards brand new Tuesday before. Go through the development by doing walk through a bunch of them myself, different languages, exercising the bacon bits case mostly, and I'll show other things, including using the microcontrollers on there, and then I'll kind of take a step back and talk. I don't have a lot. I can talk to it. In fact, I can sit here and talk about the cool things that people have made out of Beagle for full weeks straight without interruption. So we'll just schedule. And we'll dive into the labs where you'll get started and do all the stuff that I did yourself, hands-on, plus a number of extras. Questions about possible. How many of you have already done Linux before? That's a good. Has it top Linux makes my foundation. With it. So make want to call that. And where a lot of our community sits around is industrial automation type of tasks. So I meet a lot of people that do that build a lot of industrial systems and stuff using. Inspiration about how we want to go about that comes from my own personal. This is what way back when I got into computer. In front of that computer, and you know, life of things that you computer, it was all extremely hackable. I could do anything I want to except take a sledgehammer to it. Or she didn't actually want me to take a screwdriver to it at that time either. You know, that came later on. But you know, because she could take all of her important stuff and put it away in the safe, I'm going to miss work by using that computer. So want to get inspiration. And for me, I got into it. I couldn't use the computer without typing in programs. You actually had to sit there and type them in order to get the computer to actually do anything. So I wanted to play casino games, and I had that the sort of osmosis, typing these things in. You kind of understand what some of this is actually saying. Some of the odds, or I started cheating at all the casino games, and you know, my dad never knew why. I was always winning. That's because I changed the code. And it really got me going about computers, all my Radio Shack, solving these. So I want to try to reproduce for other people of any age, but in the so much to learn now, right? You know, they don't teach anymore, right? They teach them how to use Office programs, and you know, it's using computers and not actually understanding anything about how they actually work or what they do. And there's a lot of ground to cover and a lot of intimidation factor. But we really choose to focus on Linux, a lot of which because of the way it's maintained. I think a lot of you may know it's maintained with this you know, thing called Git, which keeps all the version history. Every time somebody makes a line of a change in a line of code, it's documented in the Git repo as a patch, and so we can go back and explore all of that history. And it's really trying to understand where all these things come from. You know, having that documented history is a huge point of building understanding. So we can understand about elevator algorithms. You know, we can understand why do people introduce new ones, and all the crazy fun things that that make up an operating system and really make up modern computing. If you really want to understand computers as they are today, making things affordable, you know, means that it's hackable, right? Taking taking out that the critical information that you can't live without. So if somebody crashes the hard drive, you know, making it where you're not scared of breaking it. It's replaceable. Making sure things are open all the way from boot. If you're sitting all the different talks, you're gonna be doing actually compiling the bootloaders and actually building it from mainline open source bootloaders right from the very beginning, so you can understand things very early in the system. Getting to high-level languages, I think, is really important for building understanding. I really like what a lot of people are doing with microcontrollers today, and you know, it's interesting to see some of them actually start to integrate high-level languages in the targets. But the nice thing about Linux is you basically, in whatever language you want, it's there, right? If you want Python, if you want Ruby, whatever that kind of fits your cognitive model that you can be productive in and understand, you can approach it with that. Still, it's great if you're doing anything embedded to learn C. How many of you have programmed in C in the past? Yeah. So you know that's the language you have to know, but the others are important and useful as well. At least some of them. And to motivate people with hardware, right? It's hard to compete with this idea of Halo. You know, like if somebody wants to create an application today, you know, and they're doing things on just their desktop computers, right? They see very, very rich experiences that are very, very hard to reproduce or to really augment. Yes, there's some great tool engines and stuff that kind of help, but you know, it's hard for somebody to sit down and create their first program and have it be Halo, where it's not so hard for blinking an LED or maybe turning a motor, or you know, starting to get some things, interactions of the physical world to kind of be that drug that hooks people on to computing, so they want to understand more. So our vision is to try to get things as simple to play with electronics as creating a web page. It's a concept. How many of you have written HTML? Yeah. You know, it's easy, and we'd like to try to fill in enough gaps so that making with electronics can be that way. One of our big beliefs about starting a Beagle, rather than just kind of being on somebody else's platform, I think is an important enablement for us. You know, we can put apps on our computer or apps on our phone, but it's really somebody else's platform, and it's got to multitask and do all the things that it's also supposed to do for a phone. Whereas if we make it an embedded appliance, right, we can really dedicate it to the task that we want it to do, you know, and not have it be distracted with other things. It can do what we want, where we want, how we want it, and we're in control, right? So I think that you know, creating apps is great, but better to create an appliance that actually makes the technology more welcoming in your life, rather than an extra distraction or an extra burden. And to do all of that with open source as the catalyst. All right, so open source helps enable collaboration on what's a pretty big problem, I think, when we look at like what the scope of BeagleBoard is trying to solve. We're not going to solve it ourselves. So collaborating on the problem of making embedded computing easier, making it more complete in what you can do, and it allows people coming in by doing everything in very much in the open. It allows people to come in and kind of understand where you're at, and get engaged and improve on the basics. Everybody can make a difference. So hopefully we're going to recruit many of you over the next 3 days. Yes. They're github.com/e-ale, and then it's /slides. If you go into there, there's each of the different presentations. There's slides. So this is the PocketBeagle presentation.
Let me just quickly add to that. We're still putting our infrastructure together, so things are a little bit not where they're supposed to be. Everything will be in GitHub, so It will be posted on the EL website as well as on the eLinux wiki. So we will have them in a bunch of different places that Google will find them.
Are you doing USB sticks?
We're also doing USB sticks. We are still working on it. So yeah.
I don't know how if it'll have the latest.
I want to put the slides on it as well, but we haven't recorded them yet. So.
Okay, so these slides will be on the USB stick. I think I hear myself on the microphone now. Oh. Who would do the audio here? Is Tom walk out? They're complaining about a buzz. There's a. Yeah, he turned up my gain. Maybe I should move the mic closer. Sure, but if I'm louder on the mic, then. What's the Wi-Fi? Pasadena is the password. There you go. All lowercase. So that's kind of the vision, but we're still a ways from saying that making with electronics is as easy as making a web page, right? And there are things that we could kind of try to jump to the end point a little bit to try to make things closer, but not far enough along to say like if we want to just boot to the browser and kind of make that be the user's experience. It's just too limiting for people today, and there's too many places where the people that we're collaborating with are moving in different vectors in different places. So instead of just jumping to a developer solution, here's your ready prompt, right, on this computer, we boot into Debian, right? So we've got a huge community of people helping to advance the state of the software in a lot of different ways, and actually making the programming itself being collaborative. There's a lot of different projects that have tried to create examples on like user space interfaces to all these sensors, right? So a lot of the problem that we're trying to solve is being able to control motors, read sensors, talk to different things. And there's a lot of different places where people kind of go off and do some of that stuff on their own. The place where there's really great collaboration, the place where we can actually all really work together is the Linux kernel, right? It's very organized. If we want to talk to a new device, a lot of people have this instinct to go and create a user space thing that goes and talks to it, or to otherwise kind of find a way around it. But if we put it in the kernel, we all have it, and then we have it on every platform that Linux runs on, which, as you know, is massive, right? So rather than trying to make a Beagle library to go and talk to different sensors and motors and different things, where we really are successful collaborating is when it goes into the kernel. And we'll kind of, as we get into some of the programming details, we kind of see some of the hacks and trade-offs where you can kind of do some stuff in user space and kind of do some stuff in the kernel. And there's really not one amazing development environment today for what you want to do, because a lot of it starts to get really domain specific pretty quick. So some people are really happy with command line and SSH for doing development. I happen to like the Cloud9 IDE. It gets me into the browser where I can actually run VI in my web browser. And but there's Node-RED, there's Pure Data, SuperCollider, all these graphical programming tools, LabVIEW, MATLAB. But all of these are possible to do with Beagle, right? So these are all different ways that you could be doing embedded development. Scratch and Blockly, more about learning, but potentially you could make some physically interactive things even with high-level graphical programming tools like that. And the domain-specific approaches. So we find a lot of people in our community are going and they have other distros or other things, focus points based on what they're trying to do, like MachineKit is a mill controlling. So people will use it for controlling mills, but also things like laser cutters or pick-and-place machines. And things like there's different PLC software frameworks. So people doing this ladder type of programming is something that a lot of people know in industrial control systems. So people have like toolkits for that. And then like when you look at like how to actually do the physical interconnect stuff, there's a whole bunch of different approaches for that. You know, the add-on boards for BeagleBone are called capes. You know, we're kind of leaning towards calling the add-on for the PocketBeagle pocket capes, or mini capes, but there's all sorts of other standards like microbus we'll talk more about. There's the Grove, which is this 4-wire connectors for I2C and UARTs and GPIOs and analog. There's PMOD, which has a bird right. There's dozens and dozens of these out there, and then there's like when you start trying to build up all the other stuff around it, there's a whole lot of different approaches. So those are kind of some of the barriers that kind of keep us, you know, from kind of just like solving the problem as a whole, trying to give a single point solution. But we don't want to try to go and solve all of those problems ourselves either. What we want to do is try to engage developers within the open source community to go and try to address all those needs. We try to get engaged where we really think we can help. We worked with Seed so that if you have a BeagleBone Blue, they have little adapter cables. You can directly connect the Grove connectors to the connectors on the BeagleBone Blue. So there's patch cables for that. We made PocketBeagle so that you actually the pinouts are such that you can place 2 microbus clicks on it. There's over 300. So each of these has like hundreds of different add-on things that you can sensors and controls that you can add on. Either the Grove system or the microbus system. The PocketBeagle, you can connect those directly. And then we have a growing ecosystem of people making derivative hardware and actually like working with us to make sure our software images run on that target hardware so that people have a common developer experience and kind of take that to different platforms. Things like the Beagle Logic, which is essentially a logic analyzer built around a Beagle. There's a new 3D printer controller coming out called Revolve that should be launching later this month. That's based around a Beagle, but has all the stuff for doing machine control for 3D printers or mills integrated into it. So that's kind of how we generally try to approach there's some of the things that we do to try to approach the problems that we're trying to solve. And so back in 2008, we started with the original BeagleBoard, and that was $150. Our goal was to try to get it down to below 100, but we managed to do it at 150. And then we updated it with a higher speed processor in 2010 with the BeagleBoard XM. Also in 2011, we launched that whiteboard, which is the BeagleBone, and that one was launched at $89. And then the BeagleBone Black was launched in 2013, and we were able to get it down to $45 at the initial launch, and that was really the big difference was getting from building in batches of 10,000 to getting our first order for 100,000 boards. So what really helped us right there was the launch of the Raspberry Pi, which built a lot of attention for single board computers, and so it actually increased the demand for BeagleBones quite a bit. We've taken the base BeagleBone design. We worked with a company, Octavo Systems, to put the bulk of it into a system and package, and we launched a BeagleBone Black wireless at $69. Unfortunately, it's a little bit more expensive, but it has the Wi-Fi built in, and it's using the SIP. But we took that base design, we integrated everything that you need for robotics control, and then created early last year the BeagleBone Blue. And I skipped, and actually in 2016 we launched the BeagleBoard X15, but it wasn't until kind of mid last year that it actually started being available in quantities. So that's the really high-end board, the PCI Express, SATA. It's got 2 gigabytes of RAM. It's got a whole dual gigabit Ethernet to USB 3. on it. So it's got it's kind of the everything in the kitchen sink stored in there. And this is like so we've got that as kind of our desktop replacement line. Like BeagleBoard is a kind of like fanless, low power desktop replacement style to get you kind of into embedded development. And the Beagle bones are in this Mint tin form factor, right? So all the sides of an Altoids Mint tin. And then maintaining that form factor with the CAPE support. So we're also doing some things specifically on application areas where we see a lot of users, like mobile robotics. It's a huge application area. So we put the motor controllers in here, battery management, so that there's Wi-Fi and Bluetooth, and there's sensors on here. So it's got the accelerometer, gyro, compass, and everything are all built in there. That's a ready-to-go flight controller, essentially. And then the new cool, fun thing is the PocketBeagle. So again, working with the folks at Octavo on the packaging, they took it down from a 27 millimeter package down to a 21 millimeter package, and we just stripped everything away to make the PocketBeagle. So what were our objectives with making the PocketBeagle? We wanted to get it a lot simpler. So actually leveraging how much stuff is inside that system and package, it actually makes creating a Linux computer really easy because it's almost all integrated. Essentially, you could probably debug one and make it run because all you need is a crystal, power, and power can be pretty flexible because it has its own integrated power management. So you could take a LiPo battery and just connect up to it, and a crystal, and you need some sort of boot medium, right? So you need some way to feed it data. It has a lot of, you need to kind of bootstrap there's pins that set what the boot mode is. So you need to pull those in some direction to tell it what boot mode it is, and it's going to go off chip to try to fetch its code to run at boot. And that's all you need. It's got the RAM integrated, it's got the power management integrated, the processor, all the decoupling caps and everything you need. So we wanted to try to make PocketBeagle really leverage that simplicity and demonstrate that simplicity. Make it something where people can actually take it and really modify the design, right? Really open it up to having a richer ecosystem of people making more targeted things, like the 3D printer board or the Beagle logic. We also wanted to simplify the user experience. One of the biggest headaches for users with starting with the Beagle loan is it's too flexible. And so what I mean there is each of the different pins on the header, there's a pin mux. So each of the digital pins can have one of 8 different functions. And in order to set those functions, you may have to write a little bit of device tree code or mess with a bunch of scripts, and a lot of the instructions have kind of changed. So it can be complicated to start doing that I/O because it's the defaults aren't well known, and so you have to kind of try to work your way in to try to get it configured the way you want it. So with the PocketBeagle experience, we put right on the silk screen and said, okay, this is the function that's going to boot up and run at startup, and you can just start interacting with it. So we kind of predefined the functions. Yes, you can still overwrite them, and we'll overwrite them here in this class and change it so it's still flexible. We wanted to try to make it as simple experience as possible. We really wanted to try to improve the flexibility. We put USB on the headers now because that's a nice way to do a lot of expansion on boards. Signal integrity, when you go across there, it can be a challenge, but we've not had any real issues. A lot of people have been able to successfully make USB connections on add-on boards or Pocket Capes. And one of the other challenges with the BeagleBone Black was that we reused between the original BeagleBone and the BeagleBone Black. We reused some of the pins on the header actually on the board itself for the LCD interface, for the HDMI interface, and for the eMMC flash that were both added between the white and the black. And so that meant that you had to disable those in order to use those pins. Well, nothing on the PocketBeagle is actually consumed on the board. They're all free for you to use in their mode. So no onboard board consumption. And we also didn't put the header on there by default. All your boards are going to have headers soldered on them. But if you buy a board, it won't have a header on it. It'll be just the bare, so you can put the headers on top or bottom, or even if you wanted to, you can solder it directly onto another PCB. You could actually just actually reflow it onto another PCB without even a header if you wanted. I mentioned adding the support for the 2-click boards, that the pinout and the spacing is such that you can place 2 clicks onto those boards, and I'll show off some of those later. Stuck with the Mint 10 theme. Just went from the large Mint 10 to the small Mint 10. So now the PocketBeagle is in the size of this Mint 10. That's where it gets its form factor from. And because this is I don't know if how many of you seen survival kits built on the Mint 10? Yeah. So the theme here is that computing is a necessary part of survival, and right, this is your survival kit, right? So this is something that goes in your survival kit. And we try to get things down the lowest cost as possible. There are a lot of cheap Linux computers out there. There's a lot of cheap Linux computers out there that are sold below cost. PocketBeagle is not one of those. Everybody in the chain makes a little bit of money. Yes, we don't want them to get too greedy, make too much money. Yes, but at the end of the day, if they're not making money, they might stop making it someday. And I don't want that to happen, right? We're built for longevity. So the price isn't going to go crazy. It should stay around that $25 point for 10, 20 years, right? So people can actually choose to use that, create courses like this and use them and reuse them for years, things in universities and things. Like, we want to make sure these are available for everybody. And that if you decide to create some training, you're not going to be wondering how am I going to get boards now because they stopped making them because they weren't making any money out of them. So this is sustainable. It's not you go into yes, Micro Center was selling them for $20, but that's not where it's at, right? So but it's not that you go places you can only buy one. Maybe you're familiar with another Linux board out there you can only buy one of, unless you buy the $70 kit. Anyway, key features. It's a gigahertz ARM Cortex A8 processor, so it's ARM v7, still 32-bit processor. But it runs at a gigahertz. It's dual issue superscalar. It's reasonably quick. It's not going to blaze blaze new trails, but it is far exceeds what you need for most embedded industrial type of applications. The really cool thing, of course, that's kept this processor around for a really long time is that it's got these other microcontrollers in it. Those two 32-bit PRUs are really, really powerful and flexible. They give you single cycle access to I/O pins, and they don't have any tasks that they're doing while you're running Linux. They're doing whatever they're supposed to be doing in hard real time without distractions. So they're there, and a lot of people figure out really fancy, cool ways to do things with it. They create other types of protocols that they implement. Soft peripherals. They get them to do a whole lot of stuff. I need to speed up a little bit. There's a Cortex M3 in there as well. Not a lot of people program it, but it's there for power and security. You could do all sorts of other things with it. It's got RAM. It's got 512 megabytes of RAM. It's got USB and a whole boatload of stuff in the expansion connectors that we'll talk more about. This is what the PocketBeagle looks like. There's a couple of headers. You have the boot medium off the micro SD. I talked about the boot config on there before. Those resistor packs that tells it what mode to come up in. There's the clock, the crystal. There's a power button. So if you power up off a battery, you actually need to press the power button to tell it to come up. If you press the power button while it's running, it creates a system event to tell it to shut down. So it'll be shut down gracefully. If you hold the power button for 10, 12 seconds, it'll do a hardware shutdown. So the PMIC that will detect it if it's held long enough will actually shut down directly rather than waiting for the software to do it. The USB is on the go. There's 4 user LEDs, a power LED, and not a whole lot of other stuff. There's no backside components. So it's all one-side assembly. This is what the backside looks like. I mentioned earlier about the silk screen defining the different functions. So you'll see things like, here's my SPI port. It's got chip select, clock, and everything. There's another one. I will mention that which chip select isn't actually noted there. It happens to be chip select 1 on SPI 1 and chip select 0 on SPI 0. But you've got if it's meant to be a GPIO pin by default, there's the GPIO, the kernel GPIO number. So you can just directly reference that there. The UARTs are the U's, and their port number, the transmit and receive pins. There's analog pins on here. These are all 1.8 volt, noted right there in the silk screen. There's a couple of analog pins that have resistor dividers and are connected up to GPIOs as well to do 3.3 volt. Part of that is to provide the microbus compatibility, since it needs analog and GPIO and 3.3 volt analog on the same pin for some of the clicks. There is a mistake on the silk screen. That actually should be GPIO 44. My fault, bad email. Same reason you don't have USB hubs, so bad email. Anyway, this is more the detailed view, kind of showing some of the more useful things. Each pin actually has 8 different modes, but I think we've summarized the most critical ones, so just looking at 3 of the different modes for the pins. So the analog pins are dedicated, but there are some other pins that are more flexible. Like if you wanted to use a quadrature encoder, it's available on, like, quadrature encoder 2 is available. There's the A, there's the, where's the B for, here's the B for quadrature encoder 2. It'll do hardware pulse counting if you want feedback for motor position. There's the PRU pins where it has the ultra low latency. The PRU can actually access either way, directly through its GPIOs, or through it can go through the on-chip peripheral bus and actually connect all the GPIOs, or all the peripherals for that matter as well. Ethernet is not brought out, so that's not broken out at all on the expansion header. Part of my thinking was that I wanted to reserve it so that if we did any derivatives, I wasn't potentially having people consume those pins on an add-on board. So none of like the eMMC signals were largely not brought out. So if we wanted to do a version with Flash, we wouldn't have to break the header compatibility, and as well as the Ethernet signals, we wanted to use those for something else. So I avoided bringing those out. I can't flip slides. Oh, slow flipping slides. Okay, it seems to get stuck on that slide for some reason. So this is the basic pinout of the microbus. So this is from the microbus standard. So you can see that it's got a SPI port, an I2C port, a UART, PWM, analog, all these things as their kind of their standard pinouts. There's over 300 different boards that match this configuration, and the way we did the headers is it maps out to 2 of these on our pin headers, right? So if you look at the inner rows on each side, those directly map out to microbus. So you can put one click on that side and one click on this side, and they're done from the top. Some debate whether or not some thought of whether we should put them on top or bottom. And looking back on it, maybe I probably would have flipped it over. But my sensibility at the time was to keep all the components facing the same direction. So Bacon Bits. So that is this add-on board. So I have one of the kits. It is a PocketBeagle on the bottom and a Bacon Bits pocket cape on top. That was designed specifically for this class. When did we start this development? Like maybe Michael, so Michael back there designed the Bacon Bits. When did you get started? Like 8 weeks ago? 6-8 weeks? Yeah, so maybe 5-6 weeks. I picked up the board Tuesday, so but this is all done specifically for this class. We started looking at like, okay, we want to wire this up and that up in order to talk about all the different types of interfaces. It just looked like it was going to be a lot cheaper for us to put everything on a board and build it, and you wouldn't have to worry about loose wires running all around. You just be able to plug it in and go. And that was essentially the same concept as the bacon cape that's set on the BeagleBoard Black that Dave Anders had designed. So thus the name Bacon Bits was discovered. And Bacon is also came from another board that was called a beacon, which kind of gave you something really quick to just hack an RGB LED in order to start learning some embedded Linux stuff that Dave Anders had designed. And then when he wanted to come up with something a little bit more complete as a cape, he decided that, well, dogs love bacon, so it's the bacon cape. And now we have the Bacon Bits. And so it provides us a common target for talking to all these different cool buses and avoid buying a whole bunch of different modules. So these are the key features. It includes a USB to serial, so you can see the boot console. So you can see things that are coming out UART0 right at boot. It has a USB host port on it, using the USB on there, because we don't have that host port built into to the PocketBeagle itself, because we reserve it for expansion. It satisfies it by bringing a USB host port. So it also brings out the power and reset buttons, so you can do a hardware reset. And because the cape covers up the power button, it also puts the power button on top so you can reach it. Thankfully, it goes to the header. There's a third button, which is the GPIO push button. It's the one, when you get your board, it's the one closest to the 7-segment LED. So that's the one you want to hit, is the one next to the 7-segment LED, and not the other two. Otherwise, you're going to have to wait for your code to reload. There's a thumb wheel on there for doing interaction with the ADC. There's a big tricolor LED that's currently glowing blue for me. That is connected to PWM pins, so you can learn about PWMs. There's the 7-segment LEDs are controlled by a SPI device, so you can learn how to do SPI. And then there's an accelerometer that's connected up over I2C. So you get to learn how to do all those different interfaces with this one board. Cool. I've got some stuff in here in the slides that I think is going to help for some reference. But I'm going to kind of go back and forth with actually showing you some of this stuff working. I think I'll actually just do it right here rather than. So this is where the GPIO button is connected. It's connected to P233. It's got a pull-up on it, which is really not necessary because there's pull-ups within the processor. You can turn those on and off, but it avoids you from needing to configure it. So if I go to I'll show you later how to get into this, but I wanted to just show you some actual live interactions with the board for each of these different interfaces. Let me hide the rest of this stuff for now. So just say that I'm logged in, right? But I happen to be using my web browser. I'm now logged into the board. There's this tool called config pin. We said it was P233. Is that right? So I can use config pin to give me some basic information about that pin. Were you asking me a question? It depends on that amount. I mean, it's designed to handle that amount of current for sitting at they're 5. I wouldn't drive more than 5 milliamps. I wouldn't make your design do more than 5 milliamps on these IOs. So if you just think about it as that's kind of where I put the limit. Left edge. Good. All right. So I can I can see, so it's P233 is where the button is placed. I can see that, so I can go to, in Linux, everything is a file. And that's an exaggeration, but part of what the kernel does in terms of abstraction is it gives you some standard interfaces. Read, write, control, and ioctl, right, are kind of how you talk to devices. And those things can ultimately map to the directory structure so that I can read and write these devices just through virtual files. So sysfs, how many of you have heard of sysfs, used sysfs? A bunch of you haven't. So sysfs is a virtual file system. So there's nothing sitting on my disk itself, so it's not on the micro SD card. It's just something in RAM. So I'm only talking to the kernel by talking anything into the sys directory. I can get a list of some of the different things that are mounted. So some things when I get mounted in locations. In Linux, there's a single hierarchy for like there's a single root hierarchy for any environment. So like there's one, in any place there's only one root, there's only one slash, and everything builds on top of slash. So mount tells me like what is it going on top of slash. And also tells me what slash is, right? I can find, should be able to find the root file system somewhere. Here we go, dev. So dev MMC block 0 partition 1 is my root file system, right? That's the disk that I'm actually running as my root file system. And mounting other type of things on that, I've got a sysfs entry that's handled by the kernel mounted at /sys. Anyway, so that's just talking to the kernel. When I read and write these files, it's not actually touching the disk, like, so it's not having the kernel talk to the disk, it's having the kernel talk to other hardware. So there's a GPIO class, sys-class GPIO, and we saw, let me do this config pin thing again. So config pin is a purely Beagle specific app, but it gives you some useful information about the different I/O pins. And here I'm just using it for quick reference, right? So it's telling me that the kernel GPIO ID is 45. So I need to kind of map those two together because I was looking at that location. So inside of that directory, I'll see a number of other files, including direction. We should see the direction is in, and I'm not pressing the button. Anybody guess what the value should be? Okay, I didn't hear anybody said 0. You're right, 1. It should be 1. That's what we got, 1. Good. So that's because of that pull up, right? So the voltage should be sitting at, it should be sitting at that 3.3 volts. And then when it reads over that I/O pin, I'm seeing that the value is in fact a 1. Now if I press this button, that should ground that pin, right? So it's shorting the connection between the I/O pin and ground when I'm pressing this button. Right, so it's a normally open button. When I press it, it closes it, it shorts it to ground. The voltage should now be 0. The voltage should be 0, and the GPIO value will read back as 0. Yay, we're at a GPIO. You did your first hardware, real world hardware interaction. But that's pretty significant, right? And Linux makes that really easy by turning everything into a file. The hard part, right, for us was just mapping the numbers, right? Figuring out what the I/O pin maps to actually into the software. So GPIO 45 into the Linux kernel. Well, that was easy. Let's try a little bit harder one. So this is the thumb wheel. I want to, if I'm doing my demos, I want to do one other trick because this is going to help me on this next time. I want to introduce you to this program called Watch. So Watch is just going to continuously issue this command over and over again, so I can see. So the command I want it to do is value. So Watch is going to clear the screen and run this command every so often. I don't know exactly how often. I don't remember. It's like every 0.1 seconds apparently. So every 1/10 of a second, and it's going to keep running that read. The cat is the program that's just reading the file. And so most of you are familiar with Linux, so I don't have to say that. But now if I press the button, it goes to 0. I release the button, it goes to 1. I wanted to do Watch on the GPIO because when I started doing the analog, it gets to be more interesting. All right, because we're going to be changing it constantly. Now this one, I'm just going to kind of jump. There's where that happens to live is in the subsystem called IIO. That's the I believe it's the industrial I/O subsystem in Linux. So a lot of so analog to digital converters, a lot of the sensors, a lot of those things live in this IIO world. So a whole lot of things are going to come up for you in IIO. It's a really interesting subsystem to learn more about. So I'm going to look at what devices are in IIO, and I'm looked at. I only have one. That's my only IIO device currently installed. And I look at the directory, and it looks pretty straightforward, right? Because there's a number of different in-voltage raw signals or files. Now, I think that's a little bit of a misnomer. So I put in a little extra note in here. It's connected to P119. That happens to be AIM0. All right. So if you looked at the header map, this one I don't have a nice maybe config pin might tell me that actually. I don't know if config pin will tell me that. P1 was it P119? Oh, it does. It tells me it's AIM0. So config pin would have told me this anyway. But I actually put that one on the slide. So that's 0. So the one I want to look at is in voltage 0 raw. And I think that's a bit of a misnomer because it's actually just right now what the driver is doing is actually giving it a 12-bit A to D. So you have a 12-bit number going from 0 to 4095. At 4095, you're at 1.8 volts. At 0, you're at 0 volts. So you just divide by just do the division to convert the scale to 4096. All right, so 4095 being the maximum value. So if I, obviously I don't want to sit here and turn that. So I want to just run that watch command. I don't have to keep typing every time I want to see the value change. So now I can turn the scroll wheel. So I'm going to turn all the way to one way, 4095. Turn the wheel all the way the other way. Watch it changing as it's going, and it goes down to 0. All right. Cool. So now we've done the ADC. Questions? Is this the type of stuff you were hoping to see and learn a little bit about? Yeah? Hope I'm getting into the meat of stuff right here. That just, if it's not, I'm concerned. If this isn't the meat of what you really were hoping to see. Now this one's a little bit more complicated, right? So the last two have just been inputs. We're just reading a file. There's an existing driver handling it. Here there are drivers for the RGB LED, but to sit there and try to poke everything at the command line, there's a whole bunch of different steps. And if we have in the labs, we'll try to spend some time. I'll actually try to walk you through some of all those individual steps that go on. But I'm going to jump. I'm going to jump up to JavaScript here. And I don't know why I have that one before. Oh, yeah, I do. So these are the labs that are checked in. They're in this EL codes. PWM, there we go. I don't know if my font's readable back there. Let me, it's not. Can you see the screen at all? That's too small. I'll make it bigger. Better? So here I'm going to use JavaScript. And all of this is still just doing essentially the same stuff that I was showing you, peek and poking, reading and writing files. But here I'm just using JavaScript to do all the reading and writing of files for me. And it kind of understands some of the different things it has to set up in order to actually enable the PWMs. There's actually a bug in my code as well that we get to see. So this is my program. I'm going to actually run it from the command line. So it's in. I put it in the EL. There we go. EL codes. and it's in the resources PocketBeagle when you go and look at the GitHub. So I'm going to use Node, which is a JavaScript interpreter. Everybody knows from the command lines, the first word is just the, I don't have to tell you that, is that. So Node is the interpreter that I'm going to run, and PWM.js is the program. So it's this program. That program is going to set each of the different pins to be analog outputs, which is just terminology for a PWM. And then this analog write function, this analog write function takes first argument as a pin, and the second argument is a value between 0 and 1 to say what the duty cycle of the PWM output is going to be. Now, the first time I run it, I think it should fail, because what has to happen is when we have to enable the PWM. Initially, its permissions come up as root only, and I'm actually running this as the Debian user. Did it just work for me? Oh, it just worked. How beautiful is that? So initially, it comes up as a root user. So we've created a UDEV rules. How many of you are familiar with UDEV? Some bunch of you aren't. So UDEV is a way that the kernel can notify user space of device attachments. All right. So things that have changed states. So it can notify user space so that you can do things like run scripts. And so what we've set up in the default distro is when the PWM devices, when you enable one, and all the other stuff shows up in the sysfs directories for it, it all comes up initially as root. We have a UDEV rule that actually runs a script to change the permissions to make it accessible by Debian. The JavaScript code doesn't have a good point where it waits for that. So it'll try to go and access the directories that are supposed to be created, and sometimes the first time you run it, they're not available, they're not accessible as the Debian user. So that's just something to be aware of when you're running the little JavaScript apps with the PWM, that there's a bit of a race condition because that UDEV rule has to run to change all the permissions so that you can actually get access to Debian. Does that kind of make sense? Okay. In the labs, we can kind of dive a little bit deeper into it. I'm over my time to get into the labs. Are you just waiting? I'm gonna wrap this up real quick. I'm gonna do a couple more interfaces that I'm gonna show you, and then I'm gonna turn it over to you to actually do some hands-on, and I'll show you how to get started with your board. So let me just do a couple more of these before I flip it over. I will note that, and Michael, I'll point this out to you live here now. The red and green are swapped. So because a different LED was used in what shows up on the schematic, red and green are actually swapped. So just be aware. Found that out in actually writing code. Yes? Why is there PWM red and PWM red alt? We had some debate in making the board whether or not we could just use those microcontrollers to control one of essentially one of the levels for the LED, because I wanted to try to save that pin to make we could still add clickboards. But anyway, we did it without being clickboard support, because the non-alt is a hardware PWM. The one that's actually being used, let me flip back to the slide so I can answer your question there better. The one that's actually, if you see there's a no pop on the alt, so there's actually not connected. So the one that's actually connected is the one that's on P2 pin 1. That pin happens to be used by the microbus header, so it prevents you from being able to use a connect that uses that pin, a click that uses that pin. So we just built it so Michael just added it as an option, but it's all populated, so it's just the red one it's using. So there's also a 7-segment shift register. So similar to the way everything else in Linux is exposed to this file, there's also this thing called SPI-dev. So here's where all the different pin connections are. So this thing looks like a SPI device, an SPI device, and the protocol, the wire protocol is essentially a data bit per clock. So you'll have a clock that goes up and down, and then you'll provide data out on the pins. The MOSI and MISO terms, that's master out, slave in, and master in, slave out. That's the direction of the data line. So there's one data line going from the processor to this device, and there's another data line coming from this device back to the processor. We won't be using the return data line for this example, but we need to toggle the clock. And the chip select tells it that this device is currently active. You could potentially have multiple devices on the same SPI bus, but each of them would need to have their own chip select to tell them when they're active. It also tells you when you're starting a command. So if the chip select falls low, you know that you're actually starting a new command. So I've got some more examples in here. I'm going to show you. Let me open spydev.out. So this is the SPI device. We don't have a UDEV rule to make it accessible by Debian right now. So if you want to use SPIDEV, which is the user space interface to the SPI controller, then this is you'd have to run it as root. And so each of these different /x lines, that's the commands that you want to write to the controller. So you have to look at the data sheet for that SPI device and try to figure out what that is. So the first one is essentially the address of the controller. You always put 40 on this particular SPI device. The next one is the address within the controller itself. So which register you're writing inside that controller, and then the third byte is the data value. So the 4 different commands that I've got up there, the first 2 turn on the outputs for each of the different groups. So they're grouped in groups of 8. So the first one turns on the outputs of the first 8 pins. The next one turns on the outputs for the next 8 pins. And then the last 2 commands actually set the value on those pins. So if this works right, I should be, did not want to do that. I should be displaying the value 00, because you set the I/O pins here to 0 in order to turn on the LED. Yeah. I know for one thing I checked in the wrong version because I didn't have this as bin bash, but best laid plans, right? So I've got a little bit of demoitis here. So one of the things I haven't pointed out is so what config pin is actually doing underneath the scenes a little bit. If you can use config pin. So it provides information, but you can also use it to actually set the pinmux mode. If I did something like config pin dash query P225, it says it's in SPI chip select mode. I can actually use it to change it as well. I can go config pin and set it to GPIO. Right, and the valid mode. The valid modes you can get if you get them with the dash I. Dash I. So that's the list of the different modes that you can use. The way it's actually doing is there's another thing. It gets exported to the sysfs entries, which are these pinmux helpers that we have loaded that we use to try to switch the different modes, right? So there are these files where the state of the pinmux is actually is kept, and there's a helper function, a device driver that we can use to change those different modes. So these functions are setting the different pin modes. That number's wrong. Yeah. Wow. How did this code get checked in? The chip select is 31. And turned off insert mode somehow. So chip select is 31, clock is 29, and most is 25. That will probably make a world of difference. And it did. So I've now got my 0, 0 on the display. Right. So I've now done a user space SPI dev access. I also have another example in here. We'll save that all for labs. Let me finish up the lecture. We got another 10 minutes. So for the break, you want to do another 10, 15 minutes and then the break?
Actually, people are fixing power and sound are here. So if we do it right now and then come back to do a little bit more and then do the labs,
Yeah, that's perfect. When we come back, we should be ready to do the labs.
So let's 10 minutes break. Okay. Bathrooms are upstairs. Grab coffee with Riley and come back.
Please come back, because now you actually get to play with the hardware.
You actually get to open the container to play with things. And then we'll be able to help you.
Yes, yeah, I will. Absolutely. I'll do that right now, actually. It's the one called PocketBeagle. Straight from where? SSH? Yeah, you don't have to go to, you don't have to use the IDE. Yeah, it just gives you. Oh, where did that file go? Oh, sure. I just saved it, exported it, and I don't know where it went. Ooh, that's probably not good.
We can't get this on.
Okay, we put it in the right direction.
It's out like this.
Oh, that's really wonky.
Right, that's what we're having trouble with. Yes, it's not just yours.
They're far from perfect.
No, agreed.
No, that's backwards.
No, that's correct. That's correct. They're opposite.
Oh, you're right. Okay. I just be responsible by forcing it? Is that the?
I don't know. I think Tom was trying to make a point, but I think
Okay.
I think you just made your point. So yeah, basically it should work.
Okay, cool.
Yeah.
Thank you.
Basically, it's a through-hole pin. Through-hole pins, right?
Software we needed to have pre-downloaded?
No. There's the disk should be all set up and ready to go with the stuff for the labs.
We need like to download a VM or anything like that.
You need to have Linux.
I have Linux, yeah.
Okay. And I don't think so.
Okay.
Yeah, you don't need a VM for this. If you have Linux, you can just run everything, install it natively.
Okay.
And I'm not going to have you install any stuff. I think for the other classes they will.
Okay. Thanks.
Everything I'm doing is on the board itself.
Do you guys have anything built in for stuff and bouncing? Or is that, do you kind of leave that up to the application?
Anything built in to debounce it.
Like if it's a momentary switch, does it debounce?
You can do software debouncing in the Linux kernel. I don't think Michael put any. We talked about putting in like a cap or something to kind of smooth it out.
Okay.
It depends.
Whatever you're writing, whatever you're building.
Yeah, absolutely.
Okay.
Yeah, it just depends if you need that clean of a signal. It really, I do a lot of just GPIO keys with 0 debounce and with just regular buttons. But I use the internal pull-ups, and I haven't had any problem with just using that directly to generate key events.
Okay. I was just curious about this.
E-ALE.
Okay.
E-ALE.
So why is my power not? Water. Hey, Tom. Was everybody back now?
No, everybody isn't back. I'd say
Everybody
probably,
back and everybody have kits?
well, we're working on the kits now. That's one thing. Hi there. Yes, I know. Did you register? Pre-register? Yeah. Okay, you, then the guy you want to see, where is he?
He's on his knees, or he's bent down in the back.
Everybody who paid for the kit get them.
Anybody not have their kit that paid for it?
Paid for the class. Okay, we got one person back there. Ian, one person right there. Okay, thank you. Let's see, I can't count the number of people that are here because there's so many people left. Just looking.
Sure. Those who paid.
Looks like we've got one person who's not back, two people are not back. Anybody having any trouble hearing the speaker? Can you help with that? It's all good? All right, thank you. If you want to wait for the other two people, that's free.
Maybe, well, they left their computers, so we think they're going to be back for too long. Maybe we can get started. We'll catch them up. So inside your kit, I need a slide for this. Inside your kit is the PocketBeagle with headers soldered on, so it doesn't normally come like that. A Bacon Bits mini cape or pocket cape. There's also an SD card that should already be inserted. That's also something that doesn't normally come with the PocketBeagle, so the micro SD card is added to this kit. There may also be an SD card adapter. You'll have a baggie back behind with two USB cables. One's for the PocketBeagle, the other one's for the Bacon Bits. So you can interface to the serial port. It allows you to talk to the debug console on the Beagle. For this, we won't be using the second USB cable or the USB connection on the Bacon Bits. We're only going to be connecting up over the USB on the PocketBeagle itself. So on the bottom board is the two stack. You don't want to connect these things hot. There's a potential for frying. It's very unlikely, but I would encourage you when especially if you're new to hardware, to always power off the hardware before making any modifications of connecting up the board. USB you can hot plug. It's designed for hot plugging, but for connecting the daughter board, leave it unpowered, connect it together. The orientation, I don't have a good orientation picture, but the micro USBs go in opposite directions. So that's the thing that I use when I'm connecting this to determine it. There's actually a silk screen on here that has the numbers 1 and 2, and those match to the numbers 1, the number 1 on the headers on the PocketBeagle. So that's how I figured out the orientation, is just matching up the silk screen and lining them up. We can get started in things with just the PocketBeagle, but if you want to connect up the Bacon Bits, feel free. So the developer experience is a little bit like this. BeagleBoard provides Debian images built by Robert Nelson that you can get at beagleboard.org/latest-images or this short vanity URL. We do everything. We try to enable everything to be self-hosted. A lot of people do professional development a lot of different ways, cross-building. Yocto, you're going to learn a lot of cross-building in the rest of these days, but for the rest of this class itself, we're going to use the self-hosted tools. There's tools on there for both the ARM, both of the ARMs, the A8 and the M3. We won't do any M3 code, and the PRUs. And there's libraries for the various high-level languages. The maintainer of the Python, Adafruit_BBIO library, which is the general Python library, is in the back wearing the purple shirt, works at Oshpark, Drew Fastini. So if you have any questions about the Python library, see him. If you have any questions about the JavaScript library, see me. If you have questions on Go or a billion other different languages, there's other people. There's scripts for doing a bunch of common tasks. We're going to walk through some of opt scripts. And then there's sources on there if you go into opt source once you're logged in. And there's there's servers running on there for getting access. So again, the way we look at doing development here is a single cable that USB cable is going to power, provide a network connection as well as giving the interface for developing. I don't know if it's been worth it to switch into PDF. But you can of course add networks in a whole bunch of different ways and get untethered. Normally I would say the first step is to download an image. So in addition to the two USB cables, you also have a USB to SD card adapter in there. So that, that's what allows you, you're going to plug that. You don't have to do it today because the SD cards are pre-programmed. But when you go home, you want to get the latest image. You go and download the image off of, this is the latest images site. Then you use a tool. I like Etcher. With Linux, you can also just do DD. Which is a block-by-block copy of the image, but you need to uncompress the image first. Personally, I just teach people use Etcher. It's kind of all-in-one. It helps try to prevent you from overwriting your own hard drive with the image. It won't expose your hard drive as one of the options to select. With DD, and you have to run it as root, you can very much do that. If you specify the wrong disk image, you're overwriting your hard drive, and while your host computer won't run anymore. You lost it. So bad news, don't do that. Use Etcher if you're at all squeamish. And it takes the compressed images and it writes those to the SD card itself. And then once you've got that SD card programmed, this is where we're actually going to start doing the steps together, right? So the SD card is actually inserted. It's okay to plug in your PocketBeagle. So one end of the USB cable into your computer, the other end into the PocketBeagle. And with or without the bacon bits connected, because it's useful just to get into the IDE and kind of poke around with some of that stuff first. We can always unplug it. Some people always do a soft shutdown to make sure they don't have any corrupt files. I always just pull the power. It's an ext4 file system. It's pretty robust. I almost never have any. I've never had any problems. Only occasionally I hear problems of people corrupting the exe file system. And so I would just pull the plug when I'm done. So you can always pull the plug, connect the cape, and reboot it. But anyway, you want to get booted up because what we want to really solve in here for you, the first real lab problem for you to solve is to connect up to the USB network. So the way this whole thing looks is it looks over the USB connection. It looks like there's a network device on the Beagle, and there's a network device on your computer. So that's what it looks like to your desktop computer. So when you plug it in, it's going to think that you've connected a network device. So it'll have an adapter, and it's going to try to say, oh, well, it's plugged into a network, so I'm going to do a DHCP request in order to try to get my IP address. That's what your computer should normally do when you have a new Ethernet adapter. Some of your computers may not be configured to do that automatically, so that's where having this nice interaction point is good because we can look at your system and say, okay, let's tell it to actually go and DHCP on that new adapter. And then over that network, so the Beagle, the PocketBeagle is the one providing you the address, the IP address. So it has a fixed address that's just always going to hand you the same address. There's actually two of them because for working with different operating systems, some of them work with different types of network devices better. But anyway, the one that we want is the 192.168.6.1 for our computer and 6.2 for the PocketBeagle. So the PocketBeagle will give your computer that 192.168.6.1 address, and it'll keep for itself 192.168.6.1. So when you connected to it, did anybody see a flash drive show up? Some sort of no. Some people saw it, some people didn't. If you didn't see this, it won't happen immediately. It needs for Linux to boot up. There's enough bloat at this point that it probably takes, it could take a minute or so to boot up. If it's taking more than a minute, it's taking too long. But it could be a minute or so to get that, and the device will show up. You can open that up and click the README. I thought it was pretty obvious for people to read READMEs, but apparently a lot of people don't read READMEs. Which is why we also have another copy of the same file on there called start. Just the exact same file, just to encourage you, even more. Like, is there another word we can come up with to get you to open up the file? Open or die. I like that one. So open up that one. So that's that on the left-hand side over there for you is that opened up that of start.htm or readme.htm, which is really just going to tell you to type in this magic address into your browser, right? If everything just worked, the network adapter showed up, and you got your IP address to your computer, you should just be able to type in this magic address 192.168.6.2, and it should be there. And all the other words are just ways of trying to debug if that didn't just happen for you. It should just magically happen. Has anybody already been able to browse to 192.168.6.2? A number of you have. So the magic number is too small on the screen. So let me. So that's the other one. So there's two. If you're using a Windows machine, it's going to be 7. Or a Linux machine will also see 7 as well. A Linux machine will actually see both of them. The 192.168.7.2 and 192.168.6.2, Linux will see both of them. So the one is an RNDIS driver that loads nicely on Windows. The other one's a CDC driver that loads nicely on Mac and also Linux. But on newer Linux kernels, you'll actually see both of them. It'll also have a driver that automatically gets loaded for RNDIS. In the inner browser. Yes. You can SSH into it. You can also go over the serial port, which you'll be doing, and there's a virtual serial port. There's a number of different ways, but the magic number is in the README. So if you haven't heard it, the 192.168.6.2 yet, it's in the README. So when you plug it in, you should see that flash drive. Seems like people are kind of, who is not, I know you haven't gotten the network access, who else has not gotten the network access up yet? So we have a number of people. Let me give everybody else something to do, which is to open the IDE. So the only trick right now, the trick to opening the IDE is to put :3000 after the IP address. So you put :3000 and you get into the IDE, you get to the shell. Yes, SSH is really simple. For people that are on other crazy things and not smart enough to use Linux hosts, this gives them a way to get in real easy. Who do not have network connections? Start.
We're both running.
Both running Debian. Did the network device show up? You just go to your. Oh, you do need to share the network device because you're running in a VM. Okay.
Yeah, it doesn't matter. It'll see both. Like when it, it told me at the end that this is associated with Debian.
You did.
Yeah, I mean, so it doesn't really see.
Oh, but but it needs to do each of the devices. So that's only the mass storage device. There's also a serial device. There's also a network device. The VM needs to export each of them individually.
Oh.
For my stuff, why does it say not connected? Maybe you can disconnect it from the VM. I don't know. That or the VM might be getting in the way. But it didn't even say. It said there was no cable connected. So it saw it and then maybe it took it into the VM. So where's the control for the VM that says what devices are in which? The other thing is for my stuff, you don't need Linux. You can just take it out of the VM and just use the Mac.
So I don't really know. If I stick in a device, it just it says which OS do you want to connect this device to. So I did that with the USB.
Okay. Let's just shut down your VM. Shut it down.
Okay.
And we'll just use your Mac first, and you can move ahead with that, and then we can worry about your VM for the next class. Are you going to do the same? Okay. Anybody else not getting network? So the people having network problems is to the VM so far. Anybody else having network problems getting connected? Right. That's good. So your network connection. So the magic at this point is just to, well, I shouldn't do it for you because I want to. You won't remember. But that's, you can click that and it'll take you. You actually click that link. It's actually, yeah, you can click right there and it'll take you in. It says waiting. There it goes. Who else is not in the IDE at this point? You just got here? Okay, if you signed up for the class, make sure you get a board from in back. Okay. Yeah, I'm gonna go ahead and move on, but I think you should be able to catch up just following the README. So there's a lot going on here with this USB thing. So I slow down and try to spend some time on this. I think it's kind of novel and fun and interesting, but there's certain integration challenges. So what's happening here is that we're using a Gadget driver on the Linux. So that you have the PocketBeagle is a Linux computer, but it's running Gadget drivers. And Gadget's just a term that Linux uses for things that aren't the host, right? They're the device, right? They're the device or the slave. And we can emulate a whole bunch of different types of devices. So Linux has a huge selection of Gadget drivers. And in this case, we're running a multifunction Gadget on top. So we can actually load a whole bunch of different types of gadgets kind of layered underneath it. And so all these different gadgets, most of them fall into classes. So there's classes like mass storage for a USB memory disk, or a camera for your webcam, or audio for speakers or printers, HID for your keyboard, USB keyboards or mice. So you could, if you wanted to, you could do key injection and have your PocketBeagle look like a keyboard and drive things on your host computer, look like a mouse, and take it over. It's very, very possible. So leave it as an exercise. Leave that as a longer exercise for the reader. There's some great Python scripts for doing exactly that. The session on USB is going to talk more about the USB technology and some of those. I believe that it's going to cover some of the gadgets and the host drivers as well. So some of the drivers that are available, but I haven't looked over that presentation yet. So by default, we actually set up 3 gadgets. So there's a mass storage gadget that sets up that README. So there's a file on in the disk of the system. It shares that file and makes it look like a disk on your host computer, and that serves up the README. There's a virtual serial port we can actually, which is useful in case you have any of the networking problems on your host. Actually, that's a good workaround. You can actually log in over the virtual serial connection and kind of peek and poke on the device and kind of try to figure out both ends. And then there's the virtual network that we're using. I've got a whole bunch of stuff in here on booting that's really, really useful, but I'm not gonna do that stuff now. I did want to show, I want to go some things on the tour here before diving into the programming. So let's look around the IDE a bit. Mine looks a little bit different because I have some of the EL code installed. That was also playing with the Python scripts for doing HID stuff. But you should have something that largely looks like this. So in the bottom is the command line. So this is running tmux. I don't know how many of you run tmux, or it's like screen, but it's kind of a modern version of screen. So it's running that here in your browser. So it's cursors. It's tmux is what we're running. I don't know what cursor. I know what cursors is, but I don't know what cursors is. Anyway, so there's a tmux window in here, and every time you can open up new shells in this, you can do new terminal, and you can open up new tmux sessions in here, and then you've got the text editor pane, and then a file explorer, and all of this is mounted on the disk at varlib cloud9. So that's where it sees where cloud9 is pointing. And so we've got a number of examples thrown in there. Was there a question before I go on there from there? You need to log in as Debian, and the password is temp password, TEMPPWD. And if you happen to go over the, like if I, let me log out. This is the serial session. If you happen to connect up to the serial session, it'll actually tell you on the console what the password is. So, yeah, I'm just for future reference. Let me. What's the magic for increasing the size? What is it? Control plus? Anyway, that's over this serial. This is screen, right? So I got to the serial terminal by using screen, right? I could use sudo screen and then the name of the device that showed up. I found the device by doing dmessage grep tty. Well, now there's too much junk in my log, so Chromium is overrunning my my log. Anyway, we don't need to do that. So the text editor allows you to kind of see things really quickly. There's also there's a run button up here. So there's a number of different. I'm going to show some of the hidden files here. Show hidden files. There's this integration here with C9 through these runners, so I can actually define when I click run for different file types, what it does. It's kind of a fun integration with IDE. And you'll see an auto-run folder, which there's a daemon running. If you drop a script in that folder, it'll run it on boot. So for people really, really unfamiliar with Linux, it gives them a nice handy way of just running scripts on boot up. And then there's the examples. Under the examples, we're gonna look at the PocketBeagle. And there's a number of JavaScript examples in there that you can run. The other thing I want you to look at is under extras. There's this, so to try to turn you loose on labs, there's this Bacon Cape labs. And I haven't finished transitioning all of these labs from BeagleBone Black and the Bacon Cape into PocketBeagle yet. But I think that it should be something with the information that we've given that should be fairly straightforward for you to actually go and do. So we can see, you can see different ways that you can go and access all these, the different interfaces through there. So those are the two things I want to highlight for you: is examples, extras, Bacon Cape Labs, and then the other one is this anything's in the PocketBeagle directory. So we'll go and do the other item that we have is the code that we checked in through the EAL bits. So those won't be on your drive. So I'm trying to point to things that you can, but we can reproduce them. So the first one is there's a push button demo in examples. I'm sorry. So this is examples of PocketBeagle. There's pushbutton.js. Able to find that okay? But the button is wrong. Right? The button is wrong. Right? So we need to go back to our slides, and maybe this will work better. Oh, there it is. I got lucky. This button is P233, not P23. Right. It's just a generic example. It's not. Save that. Yeah. And if you put a dot or a dash, those will work as well. It also doesn't care about case. And you can click run. Unfortunately, Node takes a really long time to start up. But when it says interrupt handler attached, you can see now I can press the button and we'll see the value toggle. Yeah. So if you don't have your Bacon bits attached, I'd say go ahead and you did the important thing, which I wanted you to do, is without the Bacon bits, which is to get into the IDE. You should now be able to unplug and connect your Bacon bits and get back into the IDE. Okay, everybody's asking orientation. The orientation, the silk screen should match up, but the easiest way visually is the micro SDs go in opposite directions. The micro USB connectors go in opposite directions. So there's a micro USB on the Bacon bits, and there's a micro USB on the PocketBeagle. So the micro USB should go opposite of each other. So the big host connector goes on top of the micro USB on the PocketBeagle, and the micro USB connection goes the opposite side. I don't know. I'd have to ask GHI. GHI soldered these together, and I think they must have hand soldered the headers. I don't know. I don't think it'll blow it up. Michael, have you looked at how the things map? If we plug it in backwards, it's not going to hurt anything, is it? It could. I mean, the power and grounds actually are symmetric. I think when you flip it, except for the one ground for USB, because of the way they're lined for clicks, they're actually symmetric when you flip them around. So I doubt anything's going to happen bad, but I don't know. So I had to go, to find the right value, actually I had to go back to the schematic of the board design. So the first thing I would notice if I tried to run something and I wasn't seeing the GPIO moving is, am I actually using the right one? And so it's useful to kind of do some stuff back from our command line stuff. So I'm going to show you some of the JavaScript stuff hands-on. But go back to config pin, right? So if we do, there's a handful of things to check when you're doing GPIO. Like one is that the right GPIO, that it's exported as a GPIO. And then you want to do things like, we found out earlier this is GPIO 45, so we need to recheck that. But there's a direction value. You're not gonna, if the direction was out, you wouldn't be able to read it. So, you know, that's a useful thing to check as direction. The pin mux is usually, if you're connected up to the right pin and you're not seeing the value change, usually the issue is the pin mux. So in this case, we've got the config pin helper. We know from the schematic that it's connected up to pin P233. And so we can look, sorry, dash Q checks what the current mode is, dash I gives the information. So we can see that that's GPIO ID, kernel ID 45. So we can double check that. It does not save if you press run. I really quickly press Control S after changing it. So if you change it and you click run, it won't save it. You lost connection? Oh, did you unplug it first? Yeah, so it's gonna have to reboot. Not rebooting? You're not seated well. Yeah, you have to push the bacon bits have to be pushed into the PocketBeagle pretty hard. Well, you're going to lose connection when you unplug it. Did you? So you're just actively using it? Oh, did you press the wrong button? So there's 3 buttons. Yeah, I forgot to recover that again because I mentioned it earlier in the lecture, but there's 3 buttons on here. The one closest to the 7-segment LED is that user button, the GPIO button. The one below that is the power button, and the one below that is the reset button. So if you press either of the 2 that aren't the user button, the user button, either of those 2 will cause it to lose connection and reboot. The middle one is the power button. If you just tap it once, it'll shut down gracefully, but it will shut down and immediately terminate the active session. Of course, the reset, there's nothing graceful about that. That's just going to immediately reset the board. Helpful buttons, but also a little bit of a risk factor for this type of lab. If you wanted to go in by SSH, if you wanted to go in by SSH, so SSH Debian, that's kind of distracting. It's the .8.6.2. The password TEMP-PWD. So everything is in var lib cloud 9. And then you go into examples, and then the overall thing, the overall labs I'd like you to kind of look at here is an extras bacon cape. There's a PDF here, and there's a number of scripts, but all of these need to essentially be changed to go along with the new hardware. If you don't have the schematic, I have all the relevant information pushed in my slides. Has everybody been able to download the slides at this point? I did a PDF version now as well. So it's github.com/e-ale, and then /slides. There's also a number of solutions under /code
PocketBeagle.pdf. I see some blinking LEDs. That makes me happy. Because I'm at this point, I need to try to figure out if I want to slow down or speed up, because I can show you some other cool stuff in here. Speed up. Oh, that's great. Yeah, no, there's I would say everybody, there's a hash Beagle. If you're on IRC, is IRC okay, or do you want Slack? IRC, so I'd say hash Beagle. On Freenode. There's also Beyond, is the EL IRC channel? Beyond, is the EALE channel open for everybody, or just developers? Okay. So actually, that's probably a better one. So for this week, if you want to chat live, I'd say so on Freenode, there's E-ALE, so irc.freenode.net. Okay. Oh, I love being able to paste if people are here. Okay, can you hear me better now without the buzz? Yeah. Yay, thank you very much. Appreciate that, guys. Great. Now I'm a little bit hot here. Let me, yeah, if we could turn it down a little bit. So if you're doing chats, this is a great place to try to collaborate, get some problems solved. This is a really great way to, if you haven't done IRC, this is a really great way to interact with the Beagle community following on. The hash Beagle seems a little bit light today, I don't know, but there's usually like around 300 people. Yeah. So maybe they're all traveling, they're not leaving stuff virtually on, but hash Beagle is a great way to get some support. I tried to idle in it. You see, even here while I was presenting, I had it up there. So, but EL is probably the best place to ask questions specific to these labs. Still a little bit loud, but I'll speak softly. So okay, we want to try to speed up a little bit to show some other cool things. I'm just going to go through some of the other things that I've got some demos for, some solutions. So thank you. If you're looking, if you can clone the code, that would be really helpful. But you can see the PWM solution there for fade. So there's a similar thing under examples. I can't even speak quietly enough. Under the different tasks there about fading a PWM. There's also this. You saw that we updated the 7-segment LEDs through using SpyDev. You could also just bit-bang them purely with GPIOs. And so you could use the shift-out function within JavaScript to essentially software emulate Spy. I cannot even speak loud enough to not get feedback.
Do you have a volume control on your package? So what I want, okay,
what I'd like to try to do, that's much better, thank you. So I want to try to go over why you've got the live boards and you can ask questions. I just full screened my console so that you can, so it's a little bit better. Let me even up the size a little bit of my font. Let's make this obnoxiously large and full size it again. I don't know how to change. Is that an option?
It was when it first started up. I don't know how to get it.
Okay, background color.
There should be a theme you can switch to.
Probably. Let me just make it darker. Better? All right, so there is, under /opt, there's a number of different directories. Really useful stuff in scripts. So under scripts, under tools, there's, once you get a network connection, so you should be able to do an internet connection sharing from your host and get the IP address from the PocketBeagle. I've been struggling to do that with Ubuntu. No problem with my Mac, but anyway, I don't have that set to show you. But if, like after you write the SD card images, if you have an SD card that's larger than what your however the 4 gig is what the images are sized for. Let's say you have an 8 gig SD card, you might want to do something like sudo grow partition. And now that's what it'll do is when it reboots, it's going to resize the partition. So there's a number of really helpful scripts like that in here. So to really grow partition, a really important one to know when you're reporting issues to the community is version. So it fetches a whole bunch of different typical configuration information for the system, like when the image was built, which version of U-boot you have installed, which version of the kernel that you're running. And then there's this interesting things with overlays. So even though try to figure out how deep to go into overlays, but so all the hardware is defined through Linux using this thing called device tree. So it gives Linux an idea of what the hardware system looks like, what things are connected up to it. There's other ways to do that, but device tree is the primary way that we do that. So there's a device tree definition for PocketBeagle. In fact, under op source, we're running the 4.9 kernel. What am I typing wrong? Oh, I put a slash at the beginning. That would break it. So, AM335X PocketBeagle. That's the name of the device tree source. So when everything boots up, so U-boot is the first thing to run, and it goes and reads a device tree file out of /boot, and the output of this source file is what it reads, and then it reads the kernel. So the bootloader U-boot reads both this device tree and the kernel, and it provides that device tree to the kernel to tell the kernel what the hardware looks like. So if we wanted to dynamically change if we want to change the hardware from what it is by default, just the baseboard, then editing this device tree is one approach that we could take. So you can see here in the file, there's everything. Well, there's an include file here actually in this one, but we see things like the SPI we have connected up to this. This is how SPI dev is loaded. So it enables these SPI dev channels that creates the user space interface to SPI. There's all those pin muxes, those drivers for the pin mux controls. That's where all these drivers are loaded and they're configured. So everything gets set up through device tree. So it's useful to kind of, over time you're going to have to learn how to edit device trees. Just working with Linux, you're going to have to. If only there was a doc. So there's a number of other useful sources here, but this is a nice way to actually run and edit the live ones. I could actually edit this and make sudo make install, and it would overwrite my. I'm going to just invoke this because I'm brave. And I know it's all good source. So this will actually build all the device trees for all the different types of boards that this image can run with, plus some others that it can't. And it'll put it into the appropriate location in the boot folder so that the bootloader can get to it. Hey there, built PocketBeagle. But a lot of the hardware, we don't want to try to edit the main file every time. So U-boot actually has the ability to edit the device tree live as it boots. So there's actually a way that you can get U-boot to make edits to it. So I've got additional files. You'll see this other repo called db.org overlays, and those are device tree overlays. For the Beagles, for all the BeagleBoard.org boards, PBs, and there's a number of these different ones for PocketBeagle. So if you see the PB at the beginning, not necessarily all of them are going to have PB at the beginning, but a lot of them do. So you'll see that there are these overlay files for these different add-on boards. So these are the clicks I keep talking about. So they look like this. So if I wanted to say add Ethernet to my PocketBeagle, I can use the Ethernet click because I've got an overlay for it, and I connect it to either. It can connect. It needs SPI. So I've got an overlay for SPI 1, and I've got an overlay for SPI 0. So depending on which way I place it, I need to pick that correct overlay. And there's this file full of environment variables that U-boot reads on boot up. So in this case, I've added one overlay to enable the PRU, which is those microcontrollers. They're not enabled by default, so I've added that in the overlay. But you'll see a number of these places where you have U-boot overlay address. Those are defined more for the BeagleBone Black, but you can on PocketBeagle you can put them right into here. You can just replace this file, remove the hash at the beginning that's for comments, and put it in here in a file that you want to load. All right, so we saw the name of the file was let's see, copy that. I could remove that. And paste that here. And now on boot, it would change the description of the hardware. U-boot would actually take that extra little chunk of device tree information and put it in there, so Linux would see that was in the system after it booted. So that would just boot up, and I would have Ethernet on my PocketBeagle now. And there's a whole bunch of other ones that you can add. Yes. Yeah. There's a great talk that was done at the last ELC. Well, this isn't ELC, but at the Embedded Linux conference on U-boot overlays. I don't know that I have anything that can really dive you into quickly, but what we can do is look at a file. I think maybe that's the. /boot/uenv.txt. So let's, yeah. Look at one of those files to get an idea of what it looks like. So you kind of have to know a little bit of, seeing a little bit of device tree to begin with. But there's, at the beginning, you'll see this extra /plugin that's telling you that it's meant to overlay an existing device tree. And then you'll see these fragments and this overlay specification. Yes? Right. So first of all, you have to understand what a device tree is. You understand what a device tree is? Sort of. So let's focus on what a device tree is and what that looks like, and then go from there to overlays. And pull up one. I don't think it's common. Let me put that. So it's a textual description. So this actually gets run through a compiler and put into a binary form that is essentially just a bunch of it's just to produce a structured data set. So that structured data defines the peripherals that are going to be instantiated by the kernel. So we say we have things like we have memory, right? So we have memory, and it lives between these addresses physically on the computer. So Linux discovers that it has memory through this mechanism. So it says I've got 512 megabytes of memory, and every peripheral. Everything in the system is done out like this. So I have an I2C controller, right? Not even the device itself. I have an I2C controller. You'd see, well, that's the pin muxes. Before I get even to the, all right. So I have an I2C controller, and I specify what's clock frequencies. This is actually referencing elsewhere, but everything in the system is described to the kernel through this set of data. So you specify what it is, and then you provide the different parameters underneath it. So like here's an I2C device. There's the EEPROM that's living within the SIP. So there's a 4K non-volatile memory inside the SIP on an I2C bus. So within I2C, I would say that this compatible line. This tells Linux which driver to load. So it's going to pull out and run that driver, and then it's going to use all these different parameters. Here, the register says that it's an I2C offset 50, and then it's providing additional base information. So it's actually defining that the data that lives in this address range is called baseboard data. And what the details are, let me show you something on the web. What the details are for that, I'm on one browser. www.kernel.org doc. In the kernel documentation, there's device tree and bindings. So all the different types of things that you can instantiate, like the EEPROM, will give you a description of how you would specify that in a device tree file, right? So what on earth am I supposed to put into this? Well, you look up the documentation for the device tree for that driver. If you don't have to read the driver itself, hopefully somebody provides you with decent documentation. That's really small print. But the important thing is that it shows you what the different compatible lines are that you need to provide, and what are the different parameters that you need to provide to that driver. So that's all in the kernel documentation folder, under documentation device tree, and then bindings. So that's it. So this is sort of a base feel to what a device tree is. Very much not PocketBeagle specific, so I didn't really plan to cover it a lot, right? So it's because I want to try to get you the different PocketBeagle specifics. But we've done some things here to try to make editing device trees and using device trees on PocketBeagle easier. We included the source for these overlays. So an overlay is something that patches a device tree. So let's use one I wrote because I might understand it a little bit better. So for instance, there's all those, so we installed all those pinmux helpers and stuff. So in the case of, I'm adding something on, the pinmux helper actually gets in the way of me taking over that pin. So what I can actually do with something with an overlay, so I create a fragment, I target it at this OCP is the on-chip peripherals of the processor where these devices have been instantiated in the existing device tree. And I created an overlay, and for each of these items, I overwrite their status with disabled. So now when the kernel boots, it actually won't load these pinmux drivers by doing this. So so I patch the device tree before the kernel even boots, because this happens in the bootloader and U-boot. There's also a way to modify it while it's running live, but maybe I shouldn't move quite that fast. Anyway, so I disabled those, all those different peripherals, and then I also disable the user space SPI driver, because I want to load a particular SPI driver. In this case, the Solomon SSD 1306, which is an LCD controller driver. And I say what pins I want to load. So the important part here, though, is that I'm able to modify the tree before it gets loaded in the bootloader. So I have the big tree that describes all my hardware, but now I've got something I've done different because I've added this other board on. I want to change that overall description to better represent my hardware, so I have to make an overlay for it. And the syntax is largely the same, except we're targeting, certain. We can either target the root to add stuff wholly new, or if I'm targeting a certain subsystem, I'm putting it under SPI. I need to do that to point to that data structure that I'm going to modify. Absolutely. It can. Well, it happens. It depends on where it reaches that point when it's kernel boot up, where it loads that driver. So it could potentially happen very quickly. I've seen cases where people can make the kernel load in tens of milliseconds. That's like hundreds of milliseconds. Let's say hundreds of milliseconds. But that's very, 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 very specialized. Typically you're going to be on the order of, half a second or so. Or a few seconds. It's not going to be milliseconds typically. It's going to be seconds typically. The bootloader is really where you want to put it if you need it really quickly. Modify the U-boot source, and you can set pinmux settings there, and GPIO settings there. Yes?
All the PocketBeagle overlays here, which one is the closest to a hello world or someone you get oriented with?
That's a good question. He's got example folder on bb.org overlays, where the Bacon Cape overlay, not the Bacon Bits, but the old Bacon Cape overlay was given as one of his examples. Actually, these things are more of examples using the boards come to think of it. I would look at that, the bacon cape overlay. So. So this is what the bacon one looks like. It's done for BeagleBone Black, so not for PocketBeagle. So there will be some changes relative to what it's actually patching, right? Because it's not patching the BeagleBone Black-based device tree; it's patching the PocketBeagle-based device tree.
Is there overlay for our bacon kit?
Not yet.
Oh.
No, I wrote one for the accelerometer, and I think I know what the bug is because they changed accelerometers between Rev 1 and Rev 0 and Rev 1. What was the other question?
I've never found a guide to the syntax of the device tree source. When what's a hash, what's an ampersand, those, sometimes it's a colon and another symbol.
Yeah. So you really need a device tree class.
Yeah, so there are an awful lot of different topics that we can cover in PIO. Device tree is certainly one that I would love to cover. At the risk of self-promotion, we do a class for embedded Linux Foundation. Literally, we do a bit on device tree that takes 4 hours. We barely scratch the surface. It's a really big surface to understand everything. So there's a number of talks at these kinds of conferences, and they always show you sort of 50 minutes of like one section of this kind of thing. What you'll find, unfortunately, is two things. First of all, the documentation for device tree isn't great, and in fact, there's a lot of disagreement over how things should be done still in device tree. The second thing is the documentation is not easily available. So most of us that have actually done the work, unfortunately, have had to learn it as we go. However, there's one thing I will tell you, and that is that the BeagleBoard board and what they do in device tree is amongst the best examples of what you can do. And in fact, we use the BeagleBone Black, and because in fact that's where a lot of this work is actually worked on. So if you want to see a really good example of how it should be done, and especially with the particular vendor that's behind the BeagleBone and how they do things, they are actually following the rules the way they are intended. So unfortunately, not a lot of great documentation. The best thing you can do is look at ETC or the device tree compiler. But we have to make some hard decisions as to what to cover during these things. I imagine in the future, maybe next year at scale, we will probably cover device tree. It is very important. The other bit is that tomorrow we are doing a I2C talk, and in fact, it is only partially I2C. In fact, the first part of it is going to get rather heavily into device model, including device tree. So I'm really hoping that my voice is being picked up.
Oh, yeah, you're not on the mic.
But yeah, unfortunately, we're not going to cover it this time round. There's just too many other really great topics. But certainly, you will find that a number of the people that are speaking for you during this series of seminars are in fact trainers, and in fact, a number of people have courses on various topics, including device tree, to say how that works. So we'll talk more about that later as well.
What's my time check?
You have until 1 o'clock.
Okay, good deal. Good. All right, so I'm gonna try to give you a little bit more example on device tree. This is a rich enough topic that it's worth a little bit more time. I do have an example that didn't work. I mentioned when I got the Rev 1 board that worked on the Rev 0. So I'm gonna try to patch it because Michael told me that what happened was they swapped the device from an let me show you what the device tree looks like. From the Freescale MMA, oh, that red is really hard to read, 8452 to the 8453. This code is checked in to the code GitHub repo, but I'm just making some changes to what's inside there, so you will have this example as part of the EL code. And so what I've done here is I've targeted I2C2. I wish I could tell you about this magic. This is magic foo that I copy repeatedly, and it screams if I don't. I have almost no a very vague idea of what that is actually doing. The parameters.
Let's please talk about that one.
You know what?
I know the answer to that. So
Yes.
yes. Okay. So maybe I'll just stand next to you so my voice gets picked up. So address cells and size cells, is that what we're talking about?
Yes.
I'm sorry. I was only barely paying attention. So address cells and size cells have to do with how things are understood in subsequent child nodes. This is a child node here, okay? And you'll see that there's a number of things in an array. Array have angle brackets like this, and inside you have a number of values. Those values are all 32-bit numbers by default, okay? And they always come in essentially groupings of address and then addresses and then a number of data. And the number of cells or entries in the array that are address, the number that are values that are then data, are specified by those two pieces of metadata. So the address cells in this case tells us that we have one cell or one entry in the array that is address and 0 data. Okay? So what this means in this case, for this particular device, is the register value, and that's what reg stands for because we all like to shorten things down to the least amount of typing, is that this is the 1C version of the address for this particular thing is 1C. If it was a CPU, typically we go 0, 1, 2, 3, 4. The address just indicates the actual thing. If it is a memory mapped device, you will find also that the address typically is the address of the thing that you're dealing with. The size tells you the size of the data. For instance, if it's a register range, what that happens to be. The other thing I will point out briefly, and it is a rule, but it is not always enforced, although newer versions of the tools are supposed to enforce it, is the first address is also used as the unit address in the actual node name. So you'll see that we have a name, and then we have @ and then a number that looks suspiciously like the register address. They're both 1C. The contrast is a bit hard to see with red on black. But essentially that's the deal. Address cells and size cells, it actually took me a really long time to learn that because, again, the documentation is terrible.
You'll also often see a label printed out ahead of this. So if you want to reference these things later on with overlays, you don't have to have a label, but it makes it a whole lot easier because that's what's being specified here with this ampersand target, is somewhere over there was a label around the node. So you can add labels to the nodes. Often the node names and the node labels are the same, but that's not at all required. They live in a different namespace, right? So the label namespace is global, whereas the node name is local, right? So that's.
So when you use an ampersand, you're referencing a label?
Yes. Yes. The ampersand is referencing a label. Where is the file at? What file? It's under, so on the GitHub, EL and code. If you go under resources, PocketBeagle, I'm going to check in a newer version after this, but you'll see this, I2C Excel.dts. This is a broken one that I was in the process of trying to figure out. Anyway, that's the file I'm editing. I've already changed it from that. We're going to try this live here. I'm going to see if this works. So I've got another little shell script in here that's going to. So we talked about how to do it in U-boot, right? You specify U-boot _ overlay. You define one of those variables, and the U-boot has this. The scripts that run in U-boot will book that and load those overlays and patch the device tree live. Well, the kernel also has a live patching mechanism. So that's exposed through config.fs. So if you go to the directory syskernel config device tree overlays, you can actually create your own overlays and modify the device tree while the kernel is running live. So the process that you follow is to make a directory. When you make a directory, some files will show up underneath it magically because it's not a real file, right? It's just like an interface to the kernel. And what I'm doing in this script is I'm actually compiling that device tree source, and I just write to it directly. So this is the DTC is the device tree compiler, and I write the output into this DTBO file, or the overlay file, that just directly writes it to the kernel. So I feed the source into the compiler into the kernel. It's 4. I don't remember where it went. This is, I think we had to backport the patch into 4. This is running 4.9. I think it was like 4.11 or so that they introduced the overlay capability. That Pentelis introduced it. That is absolutely magic. Yes. Yeah. So you can create the overlays and load them in real time. I wasn't expecting this to work, so I'm super excited. So usually the demo IDIS goes the other direction. So this is actually reading accelerometer values, and I can see now they're limited in the number of bits relative to the other device. So there's the top axis is the x-axis. So if I tilt it to the left, we can see it goes negative. If I tilt it to the right, you see it goes positive near its maximum, or to 1G value. And then the Z, if it's laying flat, you see it's kind of maximum. That's the third value. It's maximum out at Z at the sitting around 1G. If I move it up and down, you can see it changes, but it's sitting around 1G. If I flip it over, it should be about negative that value. And the same with Y, right? So Y is this direction, and then upside down is that way. So were you able to follow those patterns of the changing numbers? It's a little bit difficult to follow everything going on at once, but it's reading the accelerometer now. So it loaded the Linux device, the Linux driver for the accelerometer that's on the board, and then it automatically creates these. So the driver exposes the values, the accelerometer values, as virtual files. So let me cancel out of this.
There's a C driver somewhere that somebody wrote that knows.
In the kernel. Yes, there's a C kernel driver that knows how to read and write that accelerometer already. You'll learn how to do that in the next couple days. But so yes, that driver's already written. And most of the time when you want to add stuff, it's already somewhere there. You just have to figure out how to get it loaded, because the kernel is just chock full of interfaces for all this sorts of stuff. This is a different accelerometer than what was on the previous revision. I changed the version number, and boom, it came up. It depends. It just depends on how you compile the kernel. In our case, they're mostly modules. So if you want to find out what modules are loaded, you can do lsmod, and you can see that module was dynamically loaded. It's not pre-built into the kernel here. It was loaded.
And in the device tree where you had MMA whatever at 1C, that's an arbitrary string.
What Bian was saying was that there's looking at future tools forcing that at to be something particularly tied to it so that it's useful. Yeah, but that's news to me. As far as I know, it's arbitrary. The at does have some meaning for indexing, because you can essentially have multiple indexes of the same thing. So the at is meaningful, but what the actual number is, I don't think is meaningful. It's that reg value that's really meaningful. So in that script, remember looked earlier at the sysbus IAO devices, and there was only one of them. So when we loaded this I2C accelerometer driver, it created this other interface, and you can see all the different types of things that it has in terms of data that it's providing from the accelerometer. including things like Excel raw X values, right? And I just added that again, that same trick with the watch. In order to print all those values out in here, so I don't have to keep typing it in over and over and over again to read those values. I can just get them to display on the screen. So the terminal buffer. I'm absolutely posting the script. Hopefully you can. I'll go ahead and I'll make sure it's in. I'll make sure to post the script. Let me show this on the here. So here's the shell script. Oh, it's too hard to read. So so it reads. So the overlay is in this magic config.fs directory, right? Syskernel config device tree overlays. So I make the accelerometer directory to say that I want to provide you with a new overlay. So I do that make directory, and then here I'm writing it into the DTBO file. Right. So when I create the accelerometer directory, it creates a DTBO. Let me show you one more part of that because. Now sys kernel debug config, or no, it's there we go, kernel config device tree. What's the question? It's not on the Pocket. The code, these code examples are not on the PocketBeagle. I'll put them in for future builds, but they're not there right now. So when I created that Excel directory, it created these other files. So DTBO path status automatically. So if we cat status right now, we'll see that it actually says that the device tree overlay has been applied. So before I output that device tree overlay into this file, its status would have been I don't remember how it says its status is before, but it wouldn't be applied. Now the device tree source. So here I point to this i2c excel.dts file. That's in this repo as well. But I've made a change to it. The big change being this model number here changed. I also just removed the interrupt. So we're just polling the accelerometer at this point. There is hardware. You can configure hardware for doing the interrupts. I never actually finished figuring out all the stuff I need, all the magic foo I needed to put in here to specify the interrupts. So I was just using it by polling. So I changed that from a 2 to a 3 and then removed those two. And I'll check that in shortly. Now, so yeah, I wish I had a nice way to wrap this up, but this live kernel interface is very much the same way to kind of do the same what's done with files that are specified here, right? So we're taking these overlays, and here we're telling the bootloader to apply them while it's booting. The other way, we're just telling the kernel to hack them in while it's running. Cool. So if I specified that file here in the overlays, then every time I boot it up, that accelerometer interface will be loaded. All right. I'm trying to make sure I cover everything. I've got some details in the slides about the bootloader. This to me is useful information, you know, to try to understand a little bit more There are some pointers here also to the patches for the bootloader that we applied outside of mainline to try to handle. Like currently, our application of overlays in U-boot isn't part of mainline U-boot. That's a Beagle. The way that we're applying these overlay patches in U-boot. So the mainline U-boot has the ability to apply patches, but the fact that we use these environment variables to specify the files and apply those overlay patches, we specifically patch that into U-boot. So if you run a mainline U-boot, you would have to take some other steps to try to tell it to apply the overlay in U-boot rather than just specifying that environment variable. So, make sense? All right. Other things I want to make sure, device tree config pin. There's another really handy tool called show pins. So if you go under scripts, device, there's a Perl script that I think is really handy. It's really designed for BeagleBoard Black, but it's still really useful because it just gives you this summary of all the pins and what their current mode is, including what driver is currently controlling the pin mux.
Where are you? What did you just type?
So I'm under op scripts device bone and are in Perl showpins.pl, show-pins.pl. It's largely the same information that you can get from config pin. The nice thing is it just outputs it in a table and kind of scans across all the pins that would normally be on the BeagleBoard Black headers. You can get a more complete set by adding -v. But this parses some debug files that are provided by the kernel to specify what the current pin mux mode is. But it'll tell you the RX. So each of the pin mux controllers, if you see RX, that means the receiver is enabled. It's kind of weird. You can disable receiving on any of the I/O pins, on any of the digital I/O pins. That's a flag. The other things you can do are you can change the slew rate. So the fast, you'll see fast or slow. I think everything's set to fast slew rate, so it'll change the drive strength. If you have any noise issues on a board, you want to lower the drive strength because you just don't need the transitions to be so quick. You could actually change it to a slow slew rate. That may be something useful for GPIOs on the board. Up or down tells you whether or not a pull up or a pull down is enabled on the pin. So the internal pull up or pull down within the chip itself. The number there tells you the mux mode. So the number says so each of the different pin muxes can be either between 0, 1, 2, 3, 4, 5, 6, or 7 to say which mode is being selected on that pin, whether you're routing out the PRU signal or the GPIO signal or the SPI signal on that pin. And then you've got a description of what the active mode is. So if it's in PRU mode, if it's a SPI mode.
And that data's all baked into that script, is that right?
That's all baked into that show pin script. It's been used quite a bit. The big thing for it right now is it's for BeagleBoard Black. So if you look at the descriptions of the pins on the far left, they're not going to reflect.
But the question was, is it extracting it from the device tree?
It's not. It could be. Yeah, there's an opportunity for manual error there, but it's extracting the data that it's reading live from the kernel, the parameter values, but not the. But it's just doing table lookups to the specifics. Which one? You have to do Perl in front of it. Yeah, it doesn't have the somebody needs to chmod it. So the last thing I think I want to try to expose you guys to is the PRU. So those extra little microcontrollers. I've really messed up my view here. Where can I grab it? Can't find a place to grab to expand this. I don't think I'm cutting off anything too important on the, because I know you said it was cutting off stuff on the left. I can't grow this for some reason. All right. So there's under examples, examples, extras, PRU. I've put a couple of examples there for you. But I've got a modified version. We can run that version first. So examples, extras, PRU. So you'll see this hello PRU.PRUC. And it may not come up syntax highlighted for you by default. Or in the lower right, you can select C. You can select the syntax highlighting mode, so that syntax is at C. But I've given it a weird name because I talked earlier about the IDE having this ability to have these runners that can go off and execute scripts when you say you want to run a particular project. So I used a different file extension here to tell it how to go and run a PRU C program. So this puts a single C program, compiles it and runs it on one of those target CPUs. Just remembering one thing for you guys though, that it won't run for you by default because of the overlay stuff. I've got a script. Now I've got a command. If you're in this README, if you look at this README, there's something you can cut and paste, which is this magic sed line right here. I don't know if everybody can get to this website or not, but in the PRU examples, there's a long sed line. All this is doing is editing that /boot/uenv.txt file to load a particular overlay, because I want to load the overlay to enable the PRUs. This is the EL code repo. The path is resources PocketBeagle, and then you just scroll down. The README renders on the page. Once you run that sed line, you need to reboot, and that'll enable the PRUs for you. And if you understand sed, you can just do what it says. You don't actually have to run sed. But for folks that don't, I just try to make it easy to cut and paste. And I kind of go through the different examples that I'm going through here on the README anyway. So from that, you can just click in this IDE. Once you get the file up, you can actually just click Run. And I have to expand this. TEMP PWD. I don't know. It's a good question. Hey, brilliant. Good idea. So TEMP PWD. So it's now running, and so what that is doing is actually this user 3 LED is now being toggled by the PRU. So it's a separate processor that's actually going through the on-chip peripheral bus and toggling the GPIO for that pin. It's remote proc. It's the new one. And this, so I'm trying to give everybody a sample C template that that you can follow. I've got a bunch of crazy if-defs in here, but this code is actually pretty simple. The main routine, if you want to get to the on-chip peripherals, you need to set this bit, this control bit. So just copy that line anytime you need to get to on-chip peripherals. Any application, if you want to try to go outside of the PRU subsystem with your accesses. Otherwise, it sandboxes it, the PRUs. The hardware sandboxes them. And then I've got a silly for loop. This could just be a while one, and I'm doing GPIO set, so that is a memory mapped register defined up here. So that the hardware for the GPIOs is controlled with set and clear registers. The advantage of that is you can apply masks, right? So you can update up to 32 GPIOs at a time using masks, right? So, or you can select only certain ones to be updated. So instead of having to do a read, modify, write, you just write to either the set or clear, and use a 1 for the bits that you want to change, or a 0 for bits that you don't want to change. So if you want to clear it, you set the register bit to 1 in clear, and that's how you clear it. Does that make sense? You write a 1 instead of 0? Yeah. Maybe a little confusing. But the code here, that's what it's doing. It's writing those memory mapped registers. It's on the disk. It's examples, extras, PRU. Examples, extras, PRU, hello, PRU. And the other files that are kind of making this magic work are in the directory that are just kind of more also just boilerplate. This line is disabled right now, but if you wanted to, there's the GPIOs that are part of the PRU rather than the on-chip peripheral GPIOs. I'll try to repeat this a few times in different ways to make it make sense. So the PRU itself has GPIO pins, or GPIO outputs that the pinmux can select to put them in PRU mode, and then the PRU is in charge of those pins. Or you can have the pins go to the GPIO, which is the whole chip's on-chip peripherals GPIOs. So these registers are changing that whole chip GPIOs, right? So the same things that you'd be changing from the ARM. If you want to change the GPIOs for the PRU itself, ones that are under its control, you just use the R30 or R31 registers. R31 is for reading, R30 is for writing. They're directly mapped to processor registers. So even though this is a line of C, this is an intrinsic that specifies the actual register within the processor. So you can actually create, zero overhead loops. It's going to create a 100 megahertz waveform output if you wanted. Because you can just do an XOR of a bit and do it in an infinite loop. So you're toggling a bit at 200 megahertz. So people use this to create all sorts of cool things like Beagle logic, where he's grabbing the values of 16 data lines and shoving them off into shared memory for analysis by SIGROC, if you're familiar with SIGROC. So you can actually you can turn your PocketBeagle into a logic analyzer if you want, right? So with the GUI and everything. So I've got an additional modified version, but this should hopefully get you the idea that you can write your own C code to run on those processors. There's a linker command file in here and a make file. And so this make file is what does the compilation, right? It's just when you click the run button, it runs that make file. What was the question?
I tried the make file to type make
it won't work. The way it's done right now is that you have to specify 2 environment variables. So I'll run it from the command line now, because I've got another version. I've got another version in the EL examples that actually comprehends the bacon bits cape.
So what is the flashing? Like, what are you
Yeah, the one closest. It's toggling the blue LED closest to the USB, not the one inside. So the one inside is doing a heartbeat pattern, but if you see it, it should be toggling the one closest to the USB connector. No. If not, it's not running. It says it loaded and ran. So I've got another script that says run RGB pure U. So it does that one other step, which is making sure that the muxes are set properly. Of course, for that one, for the LED, it's not really using the muxes because it's just using it's already muxed for GPIO. But for a couple of these, a couple of the RGB LED pins are actually connected to pins that can be PRU outputs. And so I've got a modified version of the code that also sets those PRU outputs. And it's going to go through you can just run it. But here's the thing about the make file, is that you have to specify target, which is the program you want to build, and then PRU in, and specify the PRU number, if it's PRU 0 or 1 that you want it to run on. So, so instead, you can't just run make from the command line. You need to have those variables set. So if it's muxed to the PRU, you can toggle it at, it's 5 nanosecond latency from the command, right? So you could literally sit there and make a 100 megahertz waveform. If you were to do a tightest possible loop on the PRU that toggled the GPIOs, it would probably be an eighth or a tenth of that. Yeah. There's going to be some jitter when you go outside because it still has to get clock synchronized. So there will be a little bit of jitter, and there's also other bus activity when you go to the on-chip peripherals. It's going into shared buses that could take a gigahertz cycle or so of priority over the PRU accessing it. So yeah, it's definitely. You know, 100 nanoseconds is good enough, which is pretty good. If you can live with 100 nanoseconds, you can go off. So this should be okay. So I'm doing the decay thing where I go through each of the different LEDs, the different colors, and I just flash them faster and faster. So I do red, green, blue, and then white. So that example is there as a script running from the command line in the examples provided on the GitHub. What was the rest of your question?
I was asking if there was a penalty to assigning pins to the PRU with respect to other processor peripherals. Just get in the way of everything else.
The biggest thing is to make sure that the rest of you need to make sure to disable Linux. Able to keep up with all the peripherals from the PRU. If you wanted to use the PWMs or the the SPI or I2C or any of those peripherals from the PRU, they're very practical to use from that. Just make sure you disable access from the Linux so that they're not stomping on each other trying to write to registers.
I was actually asking the opposite question. So if I'm using a peripheral from the PRU, and obviously I have that peripheral disabled for Linux, is there any effect on any other peripherals?
No, the peripherals are pretty well isolated. I mean, if you start changing clocks and system clocks or other things like that, that's going to have some real impact. But if you just use the SPI1 controller, I mean, that's largely independent. You have to kind of look at the individual peripheral in some respects. Like if you end up using a channel of a PWM, that's obviously going to conflict because even though there's multiple channels, they're still controlled by the same overall, clock management and stuff that's going on for that PRU, that whole PRU PWM peripheral. So you mostly just need to apply some common sense. Is there a question back here? So at the OCP, the L3, I don't believe is fully cross-barred. I think it's going to be just block. Yeah. So there's crossbars for memory, but not for the on-chip peripheral. Yes. Yeah, they have their own target RAM. They have a shared memory area between them, but they can also access the DDR. So they, just like they can access all the on-chip peripherals, they can access the DDR. So what's really what usually to communicate with them, you'll just memory map the register, the memory space of the PRUs from the ARM, because the ARM can see the memory spaces of each of the PRUs, including their shared memory. And you would just kind of dedicate a region to write messages from the ARM each way, and you just im map that with the devmem. And I wanted to try to provide a simple example for that. There's also in the kernel there's a provision for messaging called RP message. That's very dependent on what if you're trying to. As far as cache coherency between the two CPUs, if you're going off chip, I would just say message on chip. Don't try to go through the caches. I don't know what the exact cache coherency issues would be going off chip. But for like large bulk memory sharing, it works fine. Just synchronize off elsewhere. I would synchronize in the internal memory. The code? Yeah. So the EL code will actually the code's going to be on the USB sticks tomorrow. Tomorrow, or the slides and the code are all going to be on the USB sticks? No. Sometime before the end of the week. So if you keep coming to these classes, you'll eventually get the sticks. I'm on my wrap-up slide. So you'll get the USB sticks that'll have the code on it, including. Well, I'm going to commit these changes today, so it'll be on the changes that we made here live will be on the sticks. And they're all on the GitHub. So github.com/e-ale.
Which project underneath that?
If you go to Code Resources PocketBeagle. And I'm going to update the README as well with instructions that are completely up to date for running all the different examples. Just a couple quick plugs. Hopefully you guys are going to learn so much this week. You're going to be amazing contributors, and you'll want to contribute some things back to BeagleBoard. These are kind of those critical projects. I mentioned BB alert overlays. This is where all those clickboards need support. They need love. They need overlays. Image Builder is how we put together the whole Debian image. If you need to make any changes, you want other packages included, you want to trim some stuff up, this is the place. And lastly, all those live examples that you see on the left-hand side, those all live in Bone 101. That's the repo where those all get maintained and copied. And there you can see those as the update and contribute changes and share your beautiful knowledge. We've already used our time for questions, so thank you.
Obvious one to go first because of the board we're using, but considering this is the very, very first inaugural EAL, and we're having some slight difficulties with getting things like the USB keys and stuff done, I just thank you for bearing with us. Hopefully you had a lot of fun, and all the extra information that Jason brought today, which was very much appreciated. We're now going to break until the next talk, which I believe is at 2 o'clock? Yeah, 2 o'clock, okay. And that's actually going to be my talk. We're going to be talking about kernel modules and K-builds in the kernel, and we're going to be doing that on the board itself. The USB keys are going to come eventually. Please don't leave here till Saturday evening. Please don't leave scale without coming to find one of us to get the USB key. All I can promise is that we will have them ready before the end of Saturday. Okay, and part of the problem is because literally we're all madly trying to finish this stuff. There were a lot of very last minute issues that we had to work around. So I apologize for that. But we do have a USB key for everybody. If not, all this information will be on the website. It will be in GitHub. It will be on the Linux wiki. Certainly, if you want to know for sure what's going on, we will also be emailing everybody on the mailing list that's on the EAL website. So do sign up for the emailing list there. We won't spam you. We will merely tell you what's going on that mailing list, okay? So as long as you put your name in there somewhere, we will get this information to you. And like I said, the file will be on a website as well if you don't get the USB key. Otherwise, pray for an hour. See you back here talking kernel modules. And thanks again, Kirsten.
My God, you went into the weeds so far, and everybody loved it. So that definitely shows what, where we have to go in the future.
Yeah.
The device tree was really high on my list, but it's a frustrating thing that we didn't.
We didn't cover it.
Well, we're covering so many things. So device tree is often covered in these things. I2C, SPI, and USB stuff specifically is never covered. So that's why I really covered that, but it's so hard. But honestly, the BeagleBoard stuff is still the best device tree.
Cool.
As far as everybody fighting and such, still the best. Because Panto basically still does everything on BeagleBoard. So.
That's awesome.
I know, right?
That's over in the corner in the red over there could definitely use a little bit of assistance in
Yeah.
trying to understand what's going on.
He got a little frustrated in device tree stuff.
Yes.
I think probably somebody else that's a little better.
I would love to, but I have to finish my slides. I'm actually going to skip lunch, so I'm almost done, but I have to get my labs finished. Okay.
Yeah.
I just want to see because I thought we were going to get this here, but I can't even read what's on the screen from my computer account. Some of the snippets of this could be.
The video is already online.
Yeah, but you won't be able. I can't.
And if you can't read the screen,
yeah.
you're probably not going to be able to see it from the.
Yeah, you will be able to actually read it from the video. And the reason is we do picture in picture. So we have
you got a capture of this.
We've captured that. We're actually
Beautiful.
capturing that. So the
Beautiful.
just because of that.
Yeah, that's what that's.
No, but I was telling you it's going to be right there. And by the way, a lot of people have to do that as well. It's really hard in this scenario to get it big enough.
Hi.
Yeah.
I'm wondering,
I don't know.
demo, what's that actually supposed to
We've
do?
asked that question and they really,
We're just supposed to read whether or not this button is being pressed or not.
I will talk to the venue again.
So when I run it, should I push the button?
There's no pressure at all. We will.
Yes. But not the other two, because the other two buttons will cause it to reboot. Did you change it from P3 to P33? P2 33?
2_33.
Yes.
Yeah, it should work. I mean, it's running.
And it just says 1. It just keeps printing out the number 1. Just make sure to get the right LED. That's the trick. The right button. That's the LED. that slide changes. All the changes are live in the code, right?